In the last video, we talked about terms like density and relative density. Today, let's learn about pressure. Before that, I have a question for you. Suppose you have a ball shown here, and you're taking this ball inside some fluid. This is some fluid, and the density of this fluid is rho. As you take this ball inside this fluid, my question to you is, what is going to happen to the size of this ball? Is it going to shrink, or is it going to remain of the same size, or is it going to inflate? To answer this question, we have to learn about pressure. In general day-to-day life, people confuse force with pressure. They think that pressure and force are synonymous. But speaking from physics point of view, well, they're not. In fact, pressure is defined as force per unit area. If we speak about the SI unit of pressure, then the force has a unit Newton, SI unit of Newton, CGS unit Dyne, Newton, and area is meter squared. And this quantity Newton per meter squared has a special name. It's called as Pascal. Pascal, after a scientist. The next good question to ask is pressure a scalar or a vector quantity? If I analyze it a little deeper, I would see that force is generally a vector quantity, and if force is vector divided by some scalar area, this makes pressure a vector quantity, isn't it? But the answer is no. Pressure in fact is a scalar quantity. So what we are really talking about is the magnitude of the force, not just the force, but the magnitude. And we never say that a pressure at any point is so and so in that direction. Pressure is like money. So you never say that your $100 is worth $110 in this direction and $90 in the other direction. That doesn't happen, right? If you want to define pressure at some point, let's rub this out. If I want to find out pressure at this point, let's call this P, which is H units below the surface, and let's also assume vacuum. Now I'll tell you exactly why I've taken this assumption later on. If there's air, then it will be a little different. But to understand this logic of pressure, we'll assume that there is a vacuum on the top of this topmost layer. So how do we define pressure actually? Mathematically, we assume a small area, a very small area, enclosing the point at which we want to find out the pressure. So this area, let's call this a very small area dA. This area is parallel to the surface, to the base. And what we are going to do is we are going to assume a long cylindrical column enclosing this area to the top of this vessel. So something like this. Let me try to explain why is there a force. The main reason of this force is, let's assume that this area is very, very small, so that only one molecule fits. So this is this molecule, and there will be molecule on top of it, then more, and let's assume that 4 molecules fit in this enclosed volume. Now if you think about it, this molecule is exerting the force due to its weight on this molecule, and this molecule is also doing the same and transferring the force to this molecule, and that's how the force propagates, so as to say. And on this area, the force that we are talking about is actually the force due to the weight of all the molecules above this area. Are you able to understand? That is where the force coming from, and area is our considered area, small area dA. Now to find out the pressure at this point P, and we know what force to put and what area to put. So pressure is equal to the force, which is equal to the mass into acceleration due to gravity g, divided by the small area dA. The mass of the molecules contained in this cylindrical volume is mass is density into volume, because density is mass per unit volume. So density is rho into volume is the base area into the height h into g divided by dA. And dA gets cancelled out and you have rho gh. Okay, so rho gh is actually the pressure at this point P relative to the topmost point. Okay, so this is actually the pressure difference between these 2 points P and this point on the surface S. This is the pressure difference between these 2 points. So this is actually I should write, because there is nothing on top of S, so the pressure actually at S is 0. So therefore this pressure is actually nothing but pressure at point P minus pressure at S is equal to rho g h. So the pressure between these 2 points depends upon the density of the fluid, the acceleration due to gravity, and the height by which the 2 points are separated. Furthermore, if suppose the points in consideration would have been these 2 points A and B, and they are separated by a depth of, let's say, h dash, then the pressure difference between B and A would be rho g h dash. Are you able to understand? So that's what I meant, that this is not the absolute pressure but the pressure difference, but because there is nothing on top of S, it is acting like the absolute pressure. So in this case, P at B minus P at A will be equal to rho g h dash. Okay, and why is the pressure coming into the picture? Because of the weight of the things above that point. The pressure is a scalar quantity. So suppose that there is a ball like this, and I want to find out the direction of force at each point on the surface of this ball. So the direction of force will be perpendicular to the surface on which it is acting. In this case, the direction of the force at this point will be in this direction, at this point like this. So the force will try to squeeze this ball in, right? So just understand this. Pressure is a scalar, yes, but the force that is coming due to the pressure is a vector quantity. And if you insert some object inside, then the direction of the force will be perpendicular at any point on the surface. So if you can remember this, I think it will be a lot easier for you to deal with the pressure. Now to answer the question, what is going to happen as the ball goes down, and I think you would have guessed it correctly, it would shrink, right? Because if the ball is here, then due to the pressure, there is force which is squeezing this ball in. But if you compare the force at this point and at the bottom, then you would see that because of the formula rho g h dash, the height difference increases as compared to the top of the surface. So as you go down, pressure increases, and if the pressure increases, the force will increase per unit area. Okay, so the squeezing force at the bottom is going to be more from all the directions, is going to be more as compared to the top of the surface or at any point. So as you go down, the ball will get smaller and smaller.